Welcome back to Musk's Energy Playbook, the series where we go beyond the rockets, the cars, and the headlines to understand the one thing that makes all of it possible: energy. I'm talking about the hidden infrastructure layer, the power systems, the storage networks, the microgrids that Elon Musk's companies have been quietly building for years, while the rest of the world debated whether renewables could ever be reliable enough for serious industrial work. And today, we're going to Boca Chica, Texas. While the world obsesses over Starship launches, over SpaceX's reusability records, over the next great leap to Mars, there's a story hiding in plain sight just off Highway 4, at the southern tip of Texas, right where the Rio Grande meets the Gulf of Mexico. It's the story of how SpaceX built one of the most sophisticated private energy microgrids in the United States. It's the story of how a rocket company became an energy company by necessity, by ingenuity, and by the same first principles philosophy that's defined every Musk venture. Today, we break it all down. Stick with us. This one goes deep. Before we get into Starbase specifically, let me zoom out for a moment and set the stage, because if you've been following this series, you know we've been building towards something. In episode 1, we looked at the big picture. America's energy grid is aging, underinvested, and increasingly vulnerable. AI data centers, EV adoption, and onshoring of manufacturing are all driving explosive new demand. And the grid built for a different era is struggling to keep up. In episodes 2 through 4, we examined how xAI's Colossus supercomputer in Memphis became a case study in what happens when you need enormous, reliable power right now, and the grid can't deliver it. We watched SpaceX and Tesla iterate on energy solutions across gigafactories, showing that vertical integration of energy production isn't just a nice-to-have, it's a competitive weapon. Now, in episode 5, we arrive at Starbase, arguably the most extreme test case of all, because no AI data center, no matter how power-hungry, has to contend with the raw physics of launching a 5,000-ton rocket. The energy demands here are unlike anything else in civilian infrastructure. And that's exactly why the solutions SpaceX developed here are so fascinating and so instructive for the rest of us. Let's talk about where Starbase actually is, because the location itself is the first constraint SpaceX had to solve. Boca Chica, Texas. Population essentially zero before SpaceX arrived. It sits at the very southern tip of the state, wedged between the lower Rio Grande Valley Wildlife Corridor and the Gulf of Mexico. The nearest city of any size is Brownsville, about 20 miles to the west. This is not Silicon Valley. This is not suburban Austin. There is no dense grid infrastructure here. Before SpaceX began developing the site around 2014, the existing electrical infrastructure was built to serve a handful of beach houses, a couple of shrimp boats, and not much else. Now think about what SpaceX needed to build here. Not just a launch pad, though the orbital launch pad alone is a feat of engineering. Think about everything around it. Cryogenic propellant production facilities, which require enormous, continuous power to liquefy oxygen and methane to hundreds of degrees below zero. Test stands for Raptor engines, which must be fired repeatedly, sometimes for minutes at a time. Machine shops, fabrication facilities, and an expanding workforce that needs offices, climate control, and basic utilities. And increasingly, the infrastructure for a small city, because Musk has spoken openly about building out Starbase as an incorporated Texas municipality. The power demands are staggering, and the demand profile is wildly irregular. On a normal day, Starbase might consume power at a steady industrial rate. But in the hours before a static fire test or in the critical window before a Starship launch, power consumption spikes dramatically and suddenly. The cryogenic loading systems, the pressurization systems, the ground support equipment for a vehicle the size of a skyscraper, all of it demands power simultaneously. For the main Texas grid ERCOT, this kind of erratic, high-magnitude demand from a remote location is a nightmare scenario. Texas experienced a catastrophic grid failure in February 2021 that left millions without power for days in freezing temperatures. Even in normal conditions, the transmission infrastructure serving the Boca Chica area wasn't built for heavy industrial use. So SpaceX faced a choice that increasingly large industrial operators across America are being forced to confront. Do you wait for the grid to catch up to your needs, or do you build your own? SpaceX, of course, chose to build their own. But understanding how they approached that decision tells you a lot about the broader Musk energy philosophy and why it keeps producing results that traditional utilities can't match. First principles thinking. You've probably heard the term, it's practically a Musk trademark at this point. But what does it actually mean in an energy context? It means stripping away assumptions. It means not saying we need to connect to the grid because that's how industrial facilities get power. Instead, it means asking, what do we actually need? We need electrons. We need them reliably. We need to be able to produce specific amounts on demand at specific moments. We need redundancy, because in this business, a power failure during a critical test isn't a productivity loss. It's potentially a catastrophic equipment failure or a scrubbed mission. Start there, then work backwards. When you do that, you quickly realize that a traditional grid connection, even a robust one, has fundamental vulnerabilities. Transmission lines can fail. Substations can be damaged. ERCOT can issue emergency load shedding orders. In February 2021, it did exactly that, cutting power to industrial customers first to try to protect residential supply. If Starbase had been in the middle of a critical cryogenic propellant loadup, that could have been devastating. So the SpaceX answer was a layered, redundant hybrid microgrid one that uses the main grid when it's convenient and cost-effective, but that can operate fully independently when needed. Island mode, in engineering terms. The ability to disconnect from the utility grid and keep running on local resources. This isn't a new concept in industrial energy. Data centers, hospitals, and military facilities have used backup generation for decades. What SpaceX did was take that concept and dramatically upgrade it using modern battery storage technology, advanced software controls, and a scale of solar generation that goes well beyond a simple backup system. The philosophy is the same one we saw at the Nevada and Texas gigafactories, and that we've seen across Tesla's energy division. Treat energy as a system, not a utility. A system that you design, optimize, and control, because control means resilience, and resilience means you never miss a launch window because of a power problem. So what does Starbase's energy system actually look like? Let's go layer by layer. Layer 1, solar generation. Starbase sits in Cameron County, Texas, one of the sunniest places in the continental United States. Average annual solar irradiance here is exceptional. SpaceX has taken full advantage of this by deploying extensive solar panel arrays across the site. These aren't rooftop panels. We're talking about ground-mounted utility-scale arrays that take advantage of the flat, open terrain of the South Texas coastal plain. They provide the primary daytime power generation for routine operations, lighting, computing systems, offices, machine shops, and the steady-state power needs of the facility when no major test or launch operation is underway. Solar is cheap. South Texas solar is among the cheapest electricity you can generate anywhere in the country, with capacity factors routinely above 20% and falling installed costs. For routine daytime loads, it's essentially free power once the capital is deployed. But solar is intermittent. It disappears at night. It drops during cloud cover, and it absolutely cannot, on its own, handle the sudden, massive power spikes of a Starship static fire or launch preparation sequence. That's where Layer 2 comes in. Layer 2, Tesla Megapacks. The Megapack is Tesla's utility-scale battery storage product, large modular lithium-ion battery units that can be deployed in arrays of virtually any size. Each Megapack unit stores several megawatt-hours of energy and can discharge that energy at high rates, meaning they can respond to sudden demand spikes in milliseconds. This is critical at Starbase for two reasons. First, speed. When cryogenic loading begins or a test stand fires, the power demand surge is nearly instantaneous. The grid, even a well-connected one, takes time to ramp up generation to meet sudden new demand. They go from standby to full discharge in a fraction of a second. Second, frequency regulation. One of the most destabilizing things you can do to an electrical grid is create a sudden, large load change, exactly what Starbase does regularly. Battery storage systems can counteract these load swings by absorbing or releasing energy to keep voltage and frequency stable. This protects both Starbase's own equipment and, when connected, the wider grid. The Megapack arrays at Starbase provide multiple services simultaneously. They store excess solar energy during the day, they handle peak demand spikes during operations, they provide backup power if grid supply is interrupted, and they do millisecond-level frequency regulation to keep the local microgrid stable. It's a multi-dimensional energy asset, not just a battery. Layer 3, natural gas generation. Solar and storage get SpaceX a long way, but not all the way. There are scenarios: extended cloudy weather, sustained high-load operations, prolonged grid outages where you need a generation source that can run continuously regardless of weather or state of charge. Natural gas generators fill this role at Starbase. This is a deliberate, pragmatic choice. Natural gas generation isn't clean. It produces CO2 and other emissions. In a different context, this would be a significant criticism. But in the context of building a facility that needs absolute reliability in a remote Texas location, where the alternative might be more grid dependence, it's the practical engineering answer. The gas generators serve primarily as baseload backup and emergency reserve. They run during extended operations when solar can't keep up, and they provide the ultimate safety net if both solar and storage are somehow depleted. Think of them as the insurance policy on top of the insurance policy. SpaceX has reportedly explored and may be pursuing more use of methane, specifically liquefied natural gas, or even Starship's own propellant, as a fuel source for on-site generation. This would align with the broader SpaceX vision of a methane-based space economy, and could reduce the carbon intensity of the facility's backup generation over time. Layer 4, the microgrid brain advanced software controls. This is the layer that ties everything together, and it might be the most underappreciated piece of the puzzle. A hybrid energy system with solar, batteries, and gas generators is only as good as the software that manages it. Without intelligent control, you end up with suboptimal dispatch decisions, equipment wearing out faster than it should, and critical moments where the wrong source is supplying power. Starbase's microgrid control system, developed with deep input from Tesla Energy, which supplies the Megapack infrastructure, manages all energy flows in real time. It tracks solar generation curves, battery state of charge, grid availability and pricing, and the facility's operational schedule. When a Starship test is planned for tomorrow morning, the system can pre-charge batteries to maximum during the overnight hours, set gas generators to warm standby, and pre-position the facility to handle the coming power spike without any manual intervention. When an unplanned grid disturbance hits, the system can island Starbase from the utility grid, disconnecting cleanly, switching to local supply in milliseconds, without any interruption to facility operations. From the perspective of SpaceX engineers at their workstations, the grid could be having a catastrophic failure outside the fence, and they'd never know. This is the holy grail of industrial energy resilience, and it's now operational at Starbase. Let's get specific about the most demanding energy scenario Starbase faces, because I think it illustrates just how extreme the requirements are, and why ordinary solutions were never going to be sufficient. Starship uses liquid oxygen and liquid methane as propellants. To store these fuels in liquid form, they must be maintained at extraordinarily low temperatures. Liquid oxygen at around -183 degrees Celsius, liquid methane at around -161 degrees Celsius. And for full-flow staged combustion, the engine cycle SpaceX pioneered with Raptor, the propellants are cooled even further, to deeply cryogenic temperatures that increase their density and allow more propellant to be packed into the tanks. Producing this much deeply cryogenic propellant on the ground requires enormous and sustained refrigeration and liquefaction infrastructure. These systems run continuously in the days and weeks before a launch to build up propellant inventory. But in the final hours before launch, propellant loading into the vehicle itself begins, and this is when power demand surges. The loading systems pump hundreds of tons of supercooled propellant into Starship and Super Heavy in a matter of hours. The pumps, the valves, the insulation systems, the boil-off management, all of it draws enormous power simultaneously. Estimates for the peak power demand during full propellant loading of a Starship-class vehicle range into the tens of megawatts, and this must be sustained for hours at a time. Static fire tests, When SpaceX conducts a static fire test, igniting all 33 Raptor engines on Super Heavy while holding the vehicle on the launch mount, the energy required is staggering. The water deluge system alone, the system that floods the launch mount with millions of gallons of water to absorb acoustic and thermal energy, requires enormous pumping capacity. The ignition systems, the data acquisition systems, the high-speed cameras and instrumentation, all of it spikes simultaneously. And then the engines ignite, and the facility is managing not just the electrical load, but the thermal and acoustic environment of 33 engines, producing about 7,500 tons of thrust. The monitoring systems spike. The safety systems spike. The ground support equipment for managing exhaust gases spikes. For a few minutes, Starbase is drawing power at a rate that would challenge any grid connection. Post-test recovery. After a static fire, the facility enters a different power profile, still demanding, but different. Cryogenic systems may need to rechill after the thermal event. Recovered propellant must be handled.